The General Railway Signal Company, pioneer in the development of advanced transportation systems for half a century, brings a new, highly efficient concept to modern railroad technology. A system for total computer-controlled freight classification with cybernetic controls. Through electronic technology, the nation's railroads are operating with dynamic new efficiency and speed, replacing less efficient semi-automatic controls with highly sophisticated automatic systems electronically controlled by the incredible speed and accuracy of digital computers. An exciting example of technological things to come is this advanced electronic classification facility at Selkirk, New York, near Albany. This space-age facility automatically sorts and classifies incoming freight trains, makes up new trains, and expedites freight traffic through this giant northeastern hub of the railroad system. A mighty big job, but one well-suited for modern cybernetics in terminal system design. Perlman Yard expedites eastbound carloads of fruits and vegetables, meats, building materials, general merchandise, and automobiles for delivery to New England, New York, and points south. And from the eastern seaboard, we see carloads of manufactured goods, machine tools, and clothing, classified and redirected to inland America, to the south and far west. Computerized automation at Perlman Yard delivers faster-moving freight and improves service for the entire northeastern quadrant, and its efficiency has benefited railroad economy as well, by eliminating 8 smaller obsolete classification yards. One of these, the old Selkirk facility, became the site for this huge 630-acre Perlman Yard, which stretches out for 7.5 miles. Construction of the massive electronic facility was accomplished in 2 years, without interference with train operations that could not be transferred from Selkirk. A remarkable engineering achievement made possible by the use of the most advanced earth-moving equipment, excavating 1 million cubic yards of earth. The task of the automatic graders that followed was to establish each track grade so as to get the most efficient movement of free-rolling cars into each of the 70 classification tracks, as set forth by General Railway Signal engineers. Another important job was the laying of miles of electronic cable, needed for communication and control of the network of automatic switches, retarders, detectors, and signal equipment. New techniques were employed, like the welded rail, laid in sections as long as 1,440 feet, and time-saving innovations like all welded prefabricated track panels. Over 400 track switches were installed in record time, many of them electrically operated. The giant yard required the building of several control towers. This one will house the computer and associated equipment. The heart of the system, the 70-track classification yard, expandable to 90 tracks, forms the widest section of the yard layout, which, appropriately enough, appears to take the shape of a gigantic rail spike, historic symbol of railroading. All train movements through the yard are controlled by GRS Classmatic Mark II, a total electronic system which helps make every yard move and every minute count. Cars move from the receiving yard, up the hump for inspection, over the crest to the classification yard to be sorted and made up into new trains in the departure yard. While being monitored by the yard master, the computer displays new train makeup and, at the discretion of the yard master, dispatches the train to its new destination. The digital computer communicates superbly with the human brain, answering questions and reporting instantaneously with its data displays and printouts. To GRS planners, This is the kind of performance it takes to solve the problem of moving rail freight for profit. Once a bold concept, today the GRS Classmatic system is a reality, controlling all freight movements in and out of the Pullman yard, most modern in the world. The computer system thinks of this massive operation in functional terms, dividing its work into 5 segments. It monitors and controls all train and car movements, while simultaneously providing up-to-the-minute information on displays which show the status of all phases of yard operation. It also compiles data, continuously updating its information and reports for management evaluation. Arriving ahead of the train, the advanced consist, listing all pertinent train data, is fed into the computer, whereupon the computer alerts the yardmaster. When the yardmaster is ready to assign a receiving yard track to the inbound train, he simply types his instructions to the computer. The computer system then is ready to take over the moment the train arrives, lining up and locking the assigned route into the receiving yard. Once the train is in the receiving yard, the computer is sent information on the completion of car inspection, minor repairs, air bleeding, and so on. When the display shows that the train is ready, the yardmaster commands the computer system to hump the train. Power switches automatically line up a route to the hump lead. This switch control console is used only if manual lineups should be needed. Especially helpful at night, these target lights mark the train's through route. When the route is locked, the hump conductor in the tower instructs the computer to send a radio command to the pusher engine to hump the train, and the humping procedure begins. As the leading car moves onto the hump approach, calculating proper train speed is a computer function, taking into account all important control factors to set a train speed up to 4 miles per hour. A last-minute switch or cut list, which assigns a classification track to each car, is printed out in seconds and distributed to the conductor and his humping crew. As the train of cars moves slowly up the hump approach, they are inspected visually and automatically for dragging equipment, broken wheel flanges, and for high loads. High in the main tower, the hump conductor checks off each cut as it is uncoupled. The display on his console shows him the identity of each car cut before it leaves the hump. He also has communications facilities and means for rerouting cars if necessary. There are many other push-button controls which expedite train movements through the yard. All phases of car classification proceed swiftly and efficiently. The computer system is in command all the way, controlling the routing and speed of every car, from the crest of the hump to the point of coupling. The retarder operator, located in a tower high above the classification yard, oversees the entire switching operation and is prepared to override automatic controls by operating the switches and retarders manually, should the need arise. As freight cars are pushed over the hump, the routing and the speed of each cut are accurately controlled. The computer system does this by taking measurements of weight, cut length and height, rollability, speed, and location. Then, as each car enters the retarders, its speed is reduced as required by the control factors instantly computed. In a fraction of a second, this information is balanced against other factors the computer has stored in its memory. The result, each cut of cars enters its correct classification track at a speed that will result in an acceptable coupling speed of less than 4 miles per hour. As the last car rolls over the crest, the hump conductor sends the computer any corrections he may have made in the switch list and completes the humping operation by pushing the end of train button. When all cars have reached their assigned tracks, the computer prints out a final corrected switch list. The computer's electronic brain also maintains a complete inventory by car number of every car on every classification track. It provides flash reports on misrouted cars, cars to be repaired, manual operation, elapsed time reports, and a host of other valuable information to assist yard operating and management personnel. As classification tracks fill, the terminal train master in this tower at the departure end of the yard gives his pull-out conductor routing instructions. He is in another tower where he has a good view of the switching area. He controls switches to route blocks of cars into the departure yard, where they are assembled into outbound trains. From this console, the train master, who has full control of all terminal operations, monitors train movements and track conditions in all yard areas. The display assists him by keeping him posted on the approaching trains in the receiving yard, and those being made up in the departure yard. Illuminated buttons tell him that the crew is called, brakes are tested, air okay, engine and caboose coupled, train inspection completed, train ready for departure. This successful application of cybernetics to car classification at Perlman Yard has won special attention from railroad management around the world. Well-designed automatic yards like this are efficient, can pay for themselves in a few years. Total computer control means faster-moving freight. More cars can be handled, and with more dependable schedules, and there is considerably less risk of damage to cars and loads. With the ever-increasing demand for efficient freight transportation, General Railway Signal recognizes the need for more sophisticated terminal and on-the-road control systems. Systems that can help our nation's railroads continue to grow and provide superior service to their customers. And it is with this challenge in mind that General Railway Signal continues to explore and develop the potentials that cybernetic technology holds for the railroad industry.